for what we call vibrational control system. We have time variation that we will vibrate by high frequency, but it's not only high frequency, it's also high amplitude. So high amplitude, high frequency periodic forcing. Okay? I can't apply averaging to this system because there is no epsilon in front, and even if I do my trick, which is define a time scale tau that is omega times t, so it's 1 over epsilon times t. So if I have now dx by d tau, I will have epsilon in front of everything, that's fine. But epsilon in front of this guy is okay, epsilon times this guy will not even create an epsilon, right? So we can't just apply averaging here the usual way we do. These two terms are on different time scales and also different scales, right? They're on different scales, we need to separate them. So we need a tool that separates this guy, we need separation. Okay? Any question about that? Okay, so simply, I have a differential equation in this form, f of t and x, very generic. In our system, f is not time variable. The tool that I'm going to present is very generic. F of t and x and g of t and x. Okay? And I cannot solve this differential equation for these guys combined. I want to separate them. Can I solve for f and then solve for g and combine some way? Or how can I separate these? Okay? So this is what we call the variation of constants formula. You are guys may be experts. The variation of constants formula for linear systems, this is very common, but I'm going to introduce the general version of it, the nonlinear version of it, nonlinear time varying, it doesn't matter. And this is less common, less commonly known. Interestingly, actually, its history goes back to Lagrange. In his analytical mechanics book, you will find this variation des constantes. So they were doing two-body problem. So you have the equations of motion, but then you can add a third body. So the term that's coming from the third body is supposed to be small. So it's a perturbation, small perturbation to the differential equation. So they said, okay, the way you account for this guy is to solve your main differential equation first. When you solve your main differential equation, you have constants. Any differential equation has some constants. You get it from boundary conditions or something. So he let these constants to vary. This is the name variation of constants formula. Okay? So I accounted for the perturbation in this way. Of course, I'm not going to present the Lagrange exposition of it. I'm going to present a more model exposition of it. The things here that I'm going to present, this is due to something called chronological calculus, which we will talk about in more detail next time. This is in a paper 1978 by Agrachev and Gavrilids, two Russian mathematicians, and they wrote this paper in the honor of the 70th birthday of Pontryagin. They were his students. So instead of just getting him a birthday cake, they developed the calculus, which is very useful. It's a calculus for time varying vector fields. We will talk about it next time. It's not a big deal, but actually from 78, so this is like what, 30 years, 40 years now. It has 200 citations only. It's very hard to read. But it's very fundamental. I mean, perhaps it's the only paper that provides calculus for time varying vector fields. I'm not aware of any other paper. So Boulou in 2002, he made use, this is a Siam Journal 2002, Francesco Bolu, Santa Barbara. He made use of these tools to apply, he applied these tools actually on this system, okay? Particularly the vibrational control system. So anyway, without further ado, let us see how to separate this differential equation. It's pretty general. How to do it? Well, the solution to this differential equation, x of 0 is some x 0, can be done in 2 steps. You want to decouple, right? 2 systems. Here are the 2 systems. The first system, z dot, is large f. I'm going to talk about it in a second, where you get your initial condition from the x system. The second system is just your g system, where your initial condition is what you ended up with the z. Okay? So aside from the large f, this is the decoupling, which means that if you are in that point and you want to flow along the vector field f plus g, okay? You got here, this is equivalent to flowing along some weird vector field f. So this is phi t large f, which I didn't tell you what is it now, and then continue with g. Okay? In our words, phi t f plus g is phi t large f, and then compose it with phi t g. Any questions so far?
How long do I flow along the second?
Whatever, what do you mean? It's t all over. So if you want to flow here along for 10 seconds, wait 10 seconds and then 10 seconds. Any question? Okay, so this is for all times. This is for any time. So what is f? This is what is coming from the chronological calculus. F is, I don't know if you remember this or not. What's that? Anybody remembers? What's the name of it? Pull back. It has push forward in it, but the name is the pull back of the vector field F along whatever here, which is the flow of G. Right? Here's the definition of it. It's not that fancy. You guys computed, I guess, in one of the homeworks. So F composed with phi t G, but then composed with phi t negative G here, and we need the push forward of it. And please remember that the push forward is just the Jacobian multiplying this guy. So here it's a composition of maps indeed, but here is just multiplication. This is a matrix multiplying this guy. I'm stressing it because I noticed in the homework there was an issue with the push forward. The push forward, nothing but the Jacobian, and it's indeed multiplication. Okay? And when you transfer points by maps, that's okay. When you transfer vector fields, it transfers by the Jacobian. You cannot transfer it with maps. Okay, so this is the definition of this guy. And this is a very useful tool. Why? If you have a differential equation that I cannot solve it like this, and for some reason I can play with G a lot, I can solve the flow along G only, well, you can do like this. So solve the flow along G. Solve the flow along G. Compose it with F. So here you're not solving the F differential equation at all, just applying F to a point. And then multiply by the Jacobian, which also depends on the flow of G. Everything here depends on the flow of G. If you can solve the flow along this composite differential equation now, and pass the flow of this differential equation to the flow of G again, then you got the solution of your differential equation. Okay? So sometimes it's good, and I will, in the last homework, I'll assign a problem, simple differential equation, but maybe you cannot solve it with the summation, the 2 terms, and breaking it down, it can be easy. Here, let's apply to linear systems. So let's apply this example. I have the very famous thing, ax plus bu, and I want an analytical solution for this guy, knowing that I know the analytical solution for that guy. Okay? So I'll consider this to be my G, and this to be my F. Okay? So what is phi G? Well, this is easy, e to the at from any x. right? And also the negative is easy, it's just e to the negative at times x. So what is f composed with the flow of g? Well, f is just bu, so actually the flow didn't matter at all, right? It's just a constant. It's a constant vector field, doesn't depend on x. It's just time varying, but constant with respect to x. Any issue with this statement? Don't want to make it overly simple. Okay, so I got this f. Now I need my large vector f of x or z, it doesn't matter, and it has time. This is what? This is the flow of g inverse push forward times whatever we got. So this is the flow of reverse along g. The push forward is Jacobian. Just differentiate with respect to x. So this is e to the negative at times. F composite with this guy here is du of t. So this is the large F vector field, the pullback vector field. We need to solve this differential equation and then compose it with e to the atx, right? So let's solve this differential equation. Well, it's a constant vector, it doesn't have any x. So the solution of this differential equation is the initial condition plus the integral of this guy, right? So our first system, the z system, is just z dot equals f of t and z, which is e to the negative at bu of t, subject to initial condition that is x naught, coming from the x dynamics. So the solution is easy. The solution is just whatever initial condition plus the integral of this guy, right? Because it's just a function of time and there is no x. Any question? Any question about that? And then we pass this as an initial condition to the y system. What's the y system? The y system is just g of t and y, right? Which is here, it's e to the it's just a1. With an initial condition, z of t. So that's okay. So the y of t is e to the at times z of t. Correct? Any questions? Okay, so this is e to the at x naught plus e to the at, I'm just substituting, minus tau bu of tau, which is the variation of Constant's formula that you guys are aware of. This is the common one, okay? But I just given you the very general form of it. Whether it's nonlinear, it's okay, time varying, I don't care. Okay? It's very useful tool. Okay, how is this useful to vibrational control systems? So, because this logic, typically, here is our system. Let's have fun in applying to vibrational control systems. Vibrational control systems. So systems, something like an f of x plus. This is usually the g of x times u, and u is time varying, so you put the time variation here, but we have one over x. Typically, when we apply the variation of Constant's formula, we get z dot equals f of t and z, which is f composed with phi g and the Jacobian. And then y dot is just g of t and y. Okay. The point is that I had 1 over epsilon here. Instead I have 1 over epsilon, but this now is separated. I can remove this epsilon by multiplying by epsilon squared. do the time change twice. That's fine. I can remove anything because it's stand by on its own. And here the point is, this is an integration of the G dynamics. So G has the cosines in it, cosine omega t and stuff. When you integrate any term of cosine and sine, you will get 1 over omega, right? And 1 over omega is your epsilon. So it will cancel this epsilon dynamics, and I will demonstrate it to you guys. So we separated them. This is already separate, that's fine. It will always be fine because it's on its own. But the worry was here, how do you make sure, why are you sure that we will not have mixed terms? And it's indeed the case. Let's demonstrate on the Kapitsa pendulum, see how we get it. One last thing is that typically the G has 0 mean because it has the cosines and sines inside. So when we separate it like this and take the average of both systems, this guy has a 0 average, which means that the y average is just the initial condition, which is the z. So the entire system is governed by the average of this guy, of the pullback. So the average dynamics of the entire system is just given by f bar. So get your f, get the average of it, and analyze its stability. So let's apply to the variation to the Kapitsa. So this is my system, d by dt, theta and theta dot was, this is theta dot, gives omega naught squared sine theta, 1 over epsilon. I don't remember what was it. Here, omega naught squared over delta squared. Omega naught squared over delta squared cosine omega t sine theta. So this is your G and this is your F. Okay, so let's get the flow of G. Flow along G from some point X. What is that? So I'm solving these two differential equations. I'm focusing just on G now, right? The first differential equation says x1 dot is 0. So x1 remains the same. So whatever initial condition you will have it, so this is just x1, okay? I'm moving from x1, x2 to whatever. The second differential equation now, remember this is sine theta, theta is x1. So this is sine x1. x1 is entirely constant. So this is just a number. This is a number. So the differential equation reads as x2 dot equals cosine. So just integrate.